Hello and welcome to Controllers Tech. Today we will start a new STM32 series on Modbus TCP. I have already covered a few videos on Modbus TCP with STM32, where I configured STM32 as a Modbus TCP server. But in those videos, I used the Mongoose networking library. This new series will be completely based on the LWIP library for Ethernet. We will see how to configure STM32 as a Modbus server, and later as a Modbus client as well. Before you continue with this video, I would recommend you first watch the introduction video of this Modbus TCP series. In that video, I have explained the Modbus protocol in detail, including the Modbus application data unit, the MBAP header, and the protocol data unit. I will not be going deep into the Modbus protocol basics in this video, so it will help to watch that one first. You can find it linked in the top right corner. So in this first video of the Modbus TCP series, we will see how to configure the STM32 Ethernet peripheral, and how to set up a basic Modbus server. This server will simply respond to a query from the Modbus client. We are not going to handle any function codes yet. We will just send back a basic response, so that we know the server is working correctly. As we move ahead with this series, we will keep adding different function codes to the same project. This means the project will not change, we will keep building on top of it as we go. I have already covered Ethernet configuration in a separate series, and I will refer to the first part of that series to set up Ethernet for this Modbus series as well. Here is the article on Ethernet configuration. I will use this article as a reference for the Ethernet setup in this series too. Alright, let's start STM32 CubeMX to create a new project. I am using the Nucleo H755 development board for this entire Modbus series. Let me remove all the default demo code generation, since I do not want any demo code included. Let's start with the clock configuration first. I am using the internal high-speed RC oscillator, which runs at 64 MHz. Using the PLL, we will run the system clock at 400 MHz. Now let's go back to the pin configuration and set up Ethernet. Go to the connectivity section, and under Ethernet, select the mode as RMII type. This mode depends entirely on how the Ethernet hardware is connected on your development board. You should check this in the schematic of the board you are using. In this case, the board uses the RMII type connection. You should also make sure the correct pins are used in CubeMX, because CubeMX sometimes assigns the wrong pins for the Ethernet hardware. Always compare the pins with what is defined in your board's schematic. Here, I have already checked the pins, and they are correct, so we can proceed with them. By default, Ethernet is also configured for the Cortex M4 core here. I am not going to use the M4 core at all in this project, so let me uncheck that part. Next, we need to configure UART for logging purposes. As per the schematic, UART3 is connected to the ST-Link virtual COM port. Pins PD8 and PD9 are connected to the ST-Link TX and RX pins. So we need to enable asynchronous mode for UART3, and you can see that pins PD8 and PD9 are configured automatically. I will set the baud rate to 115200, with 8 bits word length, no parity, and 1 stop bit. UART3 is also configured for the M4 core by default, so let me uncheck that as well, since we are not using the M4 core. We are also not using USB OTG in this project, so let me remove that peripheral along with its pin definitions. Alright, let's take a look at the Ethernet parameters, where we can see the memory configuration. This is exactly the same layout I explained in my Ethernet configuration tutorial, similar to how it was set up for the H755 Discovery board. Here is how the memory is laid out. The first RxDMA descriptor starts at address 3 million. From there, the Rx descriptor block begins. At an offset of 80, the TX descriptor block starts. At an offset of 100, the RX buffer starts. Each RX buffer is 1536 bytes long, and by default there are 12 RX buffers. Together, these occupy around 18 kilobytes of memory. This gives us an offset of 4900 from the start of the RX descriptor, which is where our LWIP heap will start. Now go to the middleware section and enable LWIP for the Cortex-M7 core. Under Key Options, we will configure the starting address for the LWIP heap. This should be set to the offset of 4900, right after the RX buffers. Next, we need to define the size of this heap. I am setting it to 10 kilobytes. So in total, we now have around a little more than 28 kilobytes of memory occupied, starting from address 3 million. Now let's go to the general settings and configure the IP address for the Ethernet peripheral. We are not using DHCP, so I will disable it. I am setting the IP address to 192.168.1.100, the subnet mask to 255.255.255.0, and the gateway to 192.168.1.1. That is all we need to configure here. You will notice a warning in the platform settings. This is because we need to configure the PHY. STM32 boards typically use the LAN 8742 PHY, and we need to provide the driver for it. By default, CubeMX takes this driver from the BSB, or board support package, which is why we need to configure it here. Next, let's configure the memory protection unit, or MPU. First, enable speculative access mode, along with the instruction cache and data cache. A default 4 GB memory region is already configured here. We will now enable one more region, starting at address 3 million. This is the same address where our first RX DMA descriptor begins. From this starting point, our total memory usage is around 28 kilobytes for the buffers and heap, plus another 256 bytes for the DMA descriptors. So in total, we are using close to 29 kilobytes of memory. I have already explained this MPU configuration in detail in my earlier Ethernet configuration tutorial, so we will follow the same approach here. Since 29 kilobytes does not match a standard region size, we will round it up and set the memory region size to 32 kilobytes, which is the closest available option. Set the text level to 1, with all access permitted. Instruction access should be disabled. Shareability should be enabled, and the region should not be cacheable or bufferable. Next, go to the Project Manager tab. Give this project a name, make sure the toolchain is set to STM32 Cube IDE, and click Generate Code. Now let's go to STM32 Cube IDE, and import the project. Alright, the project has been imported. Let me open the main file under the CM7 core. Here is our main file. As I mentioned earlier, I am not using the dual core setup here, so let me comment out the definition for dual core. This will hide all the dual core related functions. Let's build the project once to check that everything is fine so far. There are no errors, so we can proceed. If you look at the memory region, you will notice that RAM D2, which starts at address 3 million, is completely empty at this point. Our DMA descriptors and RX buffers are supposed to be located in this memory region, but right now they are not placed there. So we need to define these sections inside our flash script and place them into the D2 RAM. Go to the LWIP, target, and open ethernetif.c file. You will see the sections for the RX descriptors, TX descriptors, and RX pool defined there. We need to relocate these sections into the D2 RAM. I will copy the relocation settings from my earlier tutorial, and paste them into the flash script. Since the memory definition is the same, we do not need to modify anything here. Let's build the project again. Now you can see that the D2 RAM is occupied, and it shows around 18 kilobytes of usage, which matches what we expected. Now let's go back to the main file. You will notice that CubeMX only generated the LWIP initialization code, it did not generate the code to process it. So inside the infinite while loop, we need to call the function mx_LWIP process. This function handles the LWIP stack processing on every loop cycle, which is required for the Ethernet communication to keep working. Let's build the project again. There are no errors, so we are good to go. Now let's flash the project to the board. First, we will test whether we can ping the Nucleo board successfully. I have connected the Ethernet cable directly to my computer. Because of this, I need to configure my computer's Ethernet adapter to be in the same IP range as the one we configured for the Nucleo board. Here you can see the IP address is set to 192.168.1.10, and the gateway is 192.168.1.0. This is in the same range as the one we configured for the Nucleo board. Alright, the device is connected. Now let's open the terminal and ping the Nucleo board's IP address. At the moment, the ping is not working. Let me disconnect the Wi-Fi first and try again. It is still not working, so let me reset the board once. Alright, the board has been reset. Let me try the ping again. Now we are getting a ping response from the Nucleo board, which confirms that our Ethernet configuration is successful. We can now proceed with the Modbus drivers. The first thing we need to do is define a custom write function, so that all the printf data can be routed through UART3. This way, we can see the logs on the serial terminal. Now, I have already prepared a few files for Modbus. Let me copy them into our project. I am creating a new folder inside the drivers directory and naming it Modbus. We will store all our Modbus related files inside this folder, and in future videos as well, we will keep adding files here. This folder is not included in the compiler's include path by default, so we need to add it. Let's open the project properties, go to C++ build, settings, and under MCU GCC compiler, click on include paths. Here, we will add the path to the Modbus folder we just created. Click apply to add this path to our project. Now let's understand what these Modbus files are for. The file modbus.h contains the definitions of all the function codes we are going to use, along with the definitions for the exceptions. I have also defined a Modbus request structure, which holds the elements of the Modbus header and the Modbus data format. I have already explained how the Modbus format is structured in the earlier introductory video of the Modbus TCP series. Now let's look at the Modbus server.c file. This file contains the different TCP-related functions used for Modbus communication. It has the function Modbus server in it, which initializes the TCP server for the Modbus protocol. This function first creates a new TCP control block, then binds it to the IP address and the Modbus port. The Modbus TCP port is defined in the Modbus header file, and we are using port 502, which is the standard port for the Modbus protocol. After binding, the server is put into listening mode, and we set up the TCP accept callback. When a client connects to the server, this accept callback is triggered immediately. Inside this callback, we register two more callbacks, one for TCP receive, and one for TCP error. The TCP receive callback is triggered when the client sends data to the server. Inside this callback, we first call the function TCP received to inform the client that we have received a certain amount of data. This acts as a confirmation to the client. Next, we call the function pbuff copy partial to copy the data from the pbuff into our Rx buffer, which is defined inside this function. After that, we call the Modbus parser function to parse the received data. This parser function is defined inside the Modbus parser.c file, and we will look at it shortly. The TCP error callback does nothing for now. It is simply defined because the TCP protocol requires this callback to exist. Now let's take a look at the Modbus parser file. The function Modbus parser is called from the TCP receive callback, and it is responsible for parsing the received data. This function calls another function Modbus parse request. This extracts the different fields from the received data, and stores them in the correct positions inside the Modbus request structure. It basically extracts the transaction ID, the protocol ID, the length field, and the unit ID. These fields together make up the MBAP header sent by the client. It then extracts the function code, and the data, which together form the PDU, or protocol data unit. After extracting this information, we call Modbus process function to process it. This function is responsible for handling the different function codes, whether it is a request to read or write registers, coils, or inputs. All of these will eventually be handled inside this function. For now, since we are not handling any function code yet, this function will simply generate an exception for every request received from the client. The function Modbus send exception sends this exception back to the client. In our case, the exception we are sending is for an illegal function. Whether we are sending an exception or a normal response, the Modbus protocol requires the same structure. We first store 2 bytes for the transaction ID, which we copy from the received data, then 2 bytes for the protocol ID, which are always 0, then 2 bytes for the length field, 1 byte for the unit ID, 1 byte for the function code, and finally the data itself, which in this case is the exception code. Note that the function code is combined with 0x80 using an OR operation, and this is how we indicate that this is an exception response. For example, if the original function code is 3, the exception response will use function code 0x83, indicating that this is an exception for function code 3. After storing all this information in the TX buffer, we call TCP write to queue the data for transmission, and then call TCP output to actually send the data out over the network. This way, the exception response will be sent for every request, no matter what function code or request type the client sends. Now let's test if our basic Modbus server is working fine. Inside the main file, we will include the Modbus server.h header file. Then, inside the main function, after all the initializations are done, we call Modbus server init to initialize the Modbus server. That is all we need to do here. Let's build this project. Alright, the project builds fine without any errors, so let's flash it to the board. I will also open a serial terminal application to view the logs generated by the Modbus server. Let me connect to the ST-Link virtual COM port at a baud rate of 115200. Let's connect this port now. I am going to reset the board once, and you can see that the Modbus TCP server has been initialized and is now listening on port 502. Now I am using the simply Modbus TCP client to communicate with the server. I have entered the server's IP address and port. Let's connect to this server. You can see the connection is successful, and the client is now connected to the server. Here, I am setting the unit ID as 9. This is basically the ID of the slave device, and you can set it to whatever value you want. We can now test with any function code. As I mentioned earlier, the server will simply respond with an exception, no matter which function code we use. Here, I am using function code 3, requesting 10 registers starting from address 0. This is the complete request, generated by the client. Let's send it to the server. We have received a response from the server, and it is an exception. The exception code is illegal function, which is exactly how we configured our server. Now, if you look at the output log generated on the server side, you can see that the request received matches exactly what the client sent. This request is basically the Modbus Application Data Unit, or ADU, which consists of the MBAP header and the Protocol Data Unit, or PDU. The first 2 bytes are the transaction ID, which is 1. The next 2 bytes are the protocol ID, which is 0. The next 2 bytes represent the total length of the remaining data, which is 6 bytes. These 6 bytes include 1 byte for the unit ID, 1 byte for the function code, 2 bytes for the starting address, which is 0, and 2 bytes for the number of registers requested, which is 10. So the client was requesting 10 registers starting from address 0. You can see that the server has decoded the entire request correctly and printed it in the log. Since we have not defined any function code processing yet, it simply responded with the illegal function exception, which the client received correctly. So our Modbus communication is working just fine. The client is able to connect to the server, and the server is able to handle the request. Even though we have not implemented any function code handling yet, the server is still able to send a proper response back to the client. We can also try a different function code, and you will see that the response is still the same, an illegal function exception. So everything is working correctly so far. In this video, we saw how to configure Ethernet and set up a basic Modbus server on STM32, and how a client is able to send a request and receive a response from this server. In the next video of this series, we will start adding function code handling for reading registers, where we will read both holding registers and input registers. In the video after that, we will handle writing registers and coils as well. That is it for this video. I hope the explanation was clear. You can download the project from the article linked in the description. Also, feel free to leave comments if you have any doubts. Keep watching, and have a nice day.